Welcome everybody to the second Paul Bernays lecture. This second lecture by Professor Voevodsky will be about predicate logic and type theory, or it looks like the title's changed a little bit. It'll be about set theory. It'll be, at any rate, about foundations of mathematics in the present. Let me not make you wait any longer. Please, Vladimir Voevodsky, it's your turn.
Thank you, Giovanni. Hello. Thanks for coming again. As you can see, the title has changed compared to to what was in the announcement, because as I was preparing, then that's kind of what naturally fit into into the story. So it is the story of set theory. What I was able to make out of it as I was learning for these lectures. So let me first remind you what we had in the last lecture. And so in the first lecture I tried to talk a little bit about foundations of mathematics and how they relate to mathematics in general, and trying to answer the question of what is a foundation of mathematics. I came up with this observation that there seem to be two different concepts actually, which are being referred to by the same name, foundation of mathematics, and that it makes sense to distinguish these two concepts in order to make sense of the story of foundations. And these two concepts are, I just call them foundations 1 and foundations 2, where foundations 1, and this definition over here is in quotes because it's taken as it's actually a quote from Wikipedia. So the foundations 1 is about the structuring of the mathematical knowledge system and the hierarchy of mathematical concepts, while foundations 2 is about the language of mathematics and the language of mathematical reasoning, what we call mathematics. And I mentioned, I discussed some examples of how this viewpoint of foundations 1 and foundations 2 can be used to make sense of various writings about general philosophy and foundations of mathematics. So it's just kind of more fun to read it when you have this idea in mind that, okay, so let's read it and let's try to figure out which parts of it go to foundations 1 and which parts go to foundations 2. And that so I showed a little bit how foundations 1 in the ancient times, it seems that there was this Pythagorean idea of how to kind of there were two ideas. One idea was attributed to Pythagoreans, and another idea was attributed to this Geminus. These were two approaches to partitioning mathematics, to structuring mathematics. One was along the line of continuous and discrete. It's from Pythagoreans, and another one was from the line of pure and applied. That's from Geminus. And this structure of foundations 1 continued to exist with various modifications through many centuries. So about foundations 2, much less was written by mathematicians about foundations 2, because foundations 2 was like the language of mathematics was considered to be a part of the general language of logical discourse, and the general language of logical discourse was a domain of the science of logic, and the science of logic was above mathematics in the hierarchy, and so lowly mathematicians were not entitled to talk about it much. Until, of course, everything started to change, and so here we go. The first kind of the first appearance of what we today call formal logic, which I was able to find, is in the paper by George Boole. I suppose that should be the pronunciation. From 1847, which is called The Mathematical Analysis of Logic. And it's not such a big paper, and it's not such a thick paper, and it's reasonably easy to read. And Boole there, he actually says many interesting things. I mean, this is a good reference point for kind of trying to understand the flow of ideas and the flow of development, because he kind of expresses, he explains how he sees logic and how one reduces various statements in usual language into kind of the standard format of statements which are acceptable in logic. And then he proceeds to create some sort of a expression system for it. And well, I wrote it here in the slides that what he actually describes from our modern viewpoint is the logic of subclasses of one ambient class. Like, he doesn't have various sorts, for example. So everything belongs to one class of things, and everything he only talks about. His symbols are propositions, where proposition is something which distinguishes a subclass from this ambient class. And he calls these things elective symbols. There are symbols which denote the election of a set from a subclass from this ambient class. He never, however, says that he's talking about subclasses of one class. He just says a class, and then this goes on and on and on into the modern time when in Zermelo-Fraenkel theory one says something like a set without ever mentioning that it's not an abstract set but a subset of the total set of Zermelo-Fraenkel objects. So these things are already visible there, and so then there are some. So again, Boole is good because one can actually understand a little bit what was in his mind. And for example, for him, a class is a non-empty class. So at that time, it's curious how it took a long time for 0 to be accepted as a number. And it turns out that it took even longer for the empty class to be accepted as a class. So for Boole, definitely a class is a non-empty class. And for him, for example, the transformation, as he says, or deduction from all x are y's to some x are y's is a low-full transformation. So for him, for all x, x is y, implies that there exists x such as x is y. He then translates, so he translates, then he starts writing things in symbols. And something like all x are y's is written as, let's see, well, let's say everything is x or y is written as xy equals 1, right? No, xy, everything as is. Okay, let me let me just talk about what I have written here. So he translates some x r y's into a strange expression which is x y equals v, where v for him is kind of a random class, an arbitrary class. But because all his classes are non-empty, what it actually would read for us is that intersection of x and y is a class. And a class being a non-empty class, it means that intersection of x and y is non-empty. So some x are y's. And from this, but on the other hand, he uses 0 quite a bit. And he expresses the expression, assertion that no x are y's as xy equals 0. And so how does it combine? And it took me a while to kind of
I'm lost. What is x times y? Is it the logical product? Is it
sorry, that's
yes, but if one does not understand the lecture, then I think
no. Wait. Okay, let me answer. It will be faster. That's what I'm trying to explain right now. I mean, my next sentence relates to your question. So that's, if you read it, actually, it says it here. So the expression xy equals 0, which he uses to translate the proposition no x are y's, does not translate in his mind, as it does in ours, to the class of both x and y's equals the empty class. It doesn't. For him, it's a purely formal notation, which can be manipulated in a certain way, but it cannot mean for him the class of both x and y is equals to the empty class, because there is no empty class, because all classes are non-empty. So it's totally, if you think about it, it's really quite amazing that with such a, from my perspective, when I started reading it, my first impression was that this guy had kind of, there was total mess in his head. How can he write something like this and then something like this and give meaning to both things? But apparently somehow, despite of having this very strange approach to classes, where all classes are non-empty classes, he was nevertheless able to develop this calculus, and this is a remarkable achievement. And then he writes, it may happen that the simultaneous satisfaction of equations thus deduced may require that one or more of the elective symbols should vanish. That would only imply the non-existence of a class. So he says that if he has an equation and the solution of the equation requires that one of the classes which participate in the equation should contain no elements, as we would say, for him it doesn't mean that. It means that the whole thing is non-existent. So it means that the symbol itself kind of cannot be used. So that's a different meaning. And then he continues with what is probably the first formulation of the concept of inconsistency in formal logic. Somebody mentioned it yesterday about the inconsistency. Where is this whole thing? When did this? Obviously, Euclid didn't have a concept of inconsistency. He was just describing what is, and the issue of inconsistency would make no sense. It would just mean that he made some mistake in his formulation. So this issue of inconsistency can only appear in principle when the formal logic was introduced, because it's something which is inherently only belongs to the domain of formal logic. It's a property of a formal system. It's not a property of a system of thought. Well, it can be. So, and indeed, as soon as there appears some symbolic format for manipulating logical statements, there immediately appears this inconsistency, concept of inconsistency, and it's expressed in a very modern form. And it may even happen that it may lead to a final result of the form 1 equals 0, which would indicate the non-existence of the logical universe. Such cases will only arise when we attempt to unite contradictory propositions in a single equation. So that's George Boole, 1847. And that is the first appearance of inconsistency, which would be so important for later developments. Of formal inconsistency, which is that, of course, which, for example, the Gödel's theorem deals with. So the Gödel's theorem is about, one of the theorems is about impossibility of proving the negation of formal inconsistency. So a few years later, Boole wrote a book which is called The Laws of Thought. It is quite remarkable. So this original paper, the mathematical analysis of logic, is, I don't know, it's probably like 60 pages, and it's reasonably easy to really kind of, it's really easy to read through. This Laws of Thought is a book of like 350 pages. And it's very difficult to read from my point of view. And it's very difficult to get from it these ideas which were quite understandably and concisely expressed in the laws of in the mathematical analysis of logic. But there is at least one thing there which is important and new compared to the mathematical analysis of logic. There are probably more things. Of course, I didn't read the whole book of 300-something pages. And he says that every assertion that we make may be referred to one or the other of the following kinds. Either it expresses a relation among things, or it expresses or is equivalent to the expression of a relation among propositions. The former class of propositions relating to things I call primary, the later class relating to propositions I call secondary. And this is Boole 1853, and this is what later became first-order logic and second-order logic, and then, of course, higher-order logic. So it was somehow between the mathematical analysis of logic in these 6 years, he noticed that there is a difference and introduced this this concept. And he then says an interesting thing also, that any primary proposition can be transformed into a secondary proposition. If instead of the proposition the sun shines, we say it is true that the sun shines, we then speak not directly of things, but of a proposition concerning things. Every primary proposition may thus give rise to a secondary proposition. Sorry, I don't know how to pronounce this. Huh? That is, yeah, well, but there is some other... So it's fidelicet in Latin. Yes, how is it? Okay, well, namely, let's do it this way. Will give rise to a secondary, namely, to that secondary proposition which asserts its truth or declares its falsehood. So what it means is clear. I mean, he gives a clear example. Instead of saying the sun shines, we can say it's true that the proposition that the sun shines is a true proposition. So that's, and this is a distinction, and we can express it in our modern notation as a statement that P, proposition in this case, for example, the sun shines, is equivalent to the assertion that P equals true. And if you look at it, it's what's known as, well, it's actually, I guess, a slightly not completely general form of what's known as propositional extensionality in type theory. And it's something which is explicitly, for example, mentioned by by Church in his 1940 paper, which introduces the simple theory of types. He has two extensionality axioms there, and one of the axioms is precisely this one. Well, it says something slightly different. It says that P equals true is the same as P is equivalent to true. So it's a little more general statement. But in particular, the case because P is equivalent to true is equivalent to P, then the simplest case is that P is equivalent to P equals true. And this is propositional extensionality, and it's also the simplest particular case of the univalence axiom. I mean, it's kind of almost exactly the first non-trivial case of the univalence axiom. So we can trace, in that sense, univalence axiom to Boole. So that was one line of development in Foundations 2, right? So the first appearance of kind of intrusion of mathematics into the realm of logic is due to Boole, and he did a lot of things there. And so the second such fundamental advance is a paper by Gottlob Frege, which is Frege. Thank you. I'm I think pronouncing it in American style. Frege. And the paper is called "The Formula Language Modeled on That of Arithmetic for Pure Thought." So it's clearly the same line of thinking as Boole's laws of thought. And unlike Boole's paper, which is quite easy to understand, at least what easy to understand to me, Frege is much more sophisticated. And I kind of started reading it, and then I understood that I'm not going to understand it by the time when my lecture comes up. And so I put it away and decided I'll read it later and maybe comment on it in some future time. But this is certainly the most important second point in the development on Foundations 2. So this is Foundations 2. Now let's go back to Foundations 1. So while these things were happening in Foundations 2, developments also continued in what will later become the most important part of our new Foundations 1. So this general theory of forms, which Grassmann mentioned in 1844, was beginning to develop into concrete proposals, I would say. And one such discussion is Riemann's thesis, lecture actually, on the hypotheses which lie at the basis of geometry. And this is a totally remarkable paper. And how he managed to introduce so many remarkable things in 1854 without having any kind of, how he could have discussed Riemannian manifolds and metrics without even having a notion of a set, for us today looks like it couldn't be possible, but it nevertheless was possible, and he did discuss these things, and he actually discusses reasonably advanced things related to geometry. But somehow, so he also says, so he calls these things manifoldnesses. That's how it was translated into English, at least. And he says that there can be continuous and discrete, which is our most familiar distinction going back to the Pythagorean original partitioning of mathematics, or continuous and discrete, and then further partitioning. And also Grassmann, also continuous and discrete. Forms that can be continuous and discrete, and then further partitioning. So here also we have the manifoldnesses. These forms can be continuous and discrete. And then he says that kind of a lot has been said about discrete manifoldnesses. I'm not going to talk about it. I'm going to talk about continuous manifoldnesses. And so he proceeds to introduce his concept of Riemannian manifold, well, kind of metric manifoldness. So it of course somehow today it would mostly be because what we are doing is mostly like in the Univalent foundations, I would say concerns discrete manifoldnesses in our contemporary view of things. And the continuous manifoldnesses would correspond to this kind of activity which, again, Urs Schreiber likes, and this kind of synthetic differential geometry, and trying to combine the continuous, to integrate continuous into the foundations, not as a thing which is made out of many discretes, but as something which is primary and just kind of integrated on the fundamental level into the foundations. But a little later, well, kind of 30 years later, there is a paper by George Cantor, which is nowadays, the title is translated as Foundations of the General Theory of Manifolds, and here the word manifold in German is this one. I haven't checked which one. I haven't put in here what was the German word that Riemann used. So Cantor explained. I don't know.
One of the two.
Well, as you can see here, it is this. So it's not one of the two.
Well, Lehre ist just teaching. Manifaltigkeit is
So Cantor explains the word manifold as follows. So I use this word to designate a very broad theoretical concept which I hitherto used only in the special form of a theory of geometric or arithmetical sets. In general, by a manifold or set, I understand every multiplicity which can be thought as one. So this very well applies to what we today call a type. A type is every multiplicity which can be thought of as one. Every time you can think of something as forming a unit in some composite sense, you can think of it as a type. Remember, we actually had a question yesterday: what is the type to which foundations belong to? So can we say that foundations is an object of this type, and can we formally describe that type? So that would be an example. So foundations here would be an object of a very kind of complex of multiplicity of all possible foundations with very complex structure, and we can still think about about making a type whose objects will be foundations. And so what we call today, I think Cantor would he would probably be surprised at the generality of our concept of a type, but I think he would he would like the idea that what he was trying to develop is how we can think about it. So there is another thing. If you read a little further, I didn't include it here, but Cantor further writes in this same paragraph, and you can find it out easily, that he thinks, he feels, that what he's doing is that he's developing a general theory of Platonic eidos or ideas. Now, eidos is translated in modern philosophy is most oftenly translated into English as form. So the translation of that would be that he's feeling that what he's trying to develop is a general theory of forms, which would just go very well with what Grassmann had said. And that's what I feel, and I will be arguing more and more about it later, that what we're doing with univalent foundations, we're continuing this tradition, which developing this yet another, I mean, now more advanced version of this general theory of forms. And now also this Cantor's paper contains a totally remarkable paragraph, which I really liked very much. Mathematics is in its development entirely free and is only bound in the self-evident respect that its concepts must be both consistent with each other and also stand in exact relationships, ordered by definitions to those concepts which have previously been introduced and are already at hand and established. So this is Cantor's view, which I very much, which I find very, very modern. And then there are words which, and there is expression, sorry, and then there is something which Boole writes in his Laws of Thought. And he says that it's also true about mathematics that an almost boundless diversity of theorems which are known and an infinite possibility of others as yet unknown rest together upon the foundation of a few simple axioms. And I want to contrast these two viewpoints. So the Boole's viewpoint is we'll have these few axioms, few kind of basic notions, and then we'll build all of the mathematics by kind of formal generation from these things. Cantor says something different. He says we'll be building mathematics as it goes, and we'll of course have to take care of being precise in what we're saying, and also about looking for inconsistencies. But other than that, we will be free. And of course, as we'll see, actually, I think this is what I'm going to go to. We basically now know that this second approach is not really feasible because of the Gödel's theorem. So theorems. I mean, the approach is feasible for some partial theories, but not for everything. So then the following happened, again, from my point of view. So there were these two, in a sense, contrasting approaches, and there was this kind of Platonic Pythagorean idea of this general theory of forms, and Grassmann, and then Riemann, and then Cantor, and they were all kind of trying to see this new mathematics and new theory in new theory of forms. And then there was a development of foundations too, which introduced this formal language and kind of introduced mathematics into logic, and so the formalization became a possibility. And then they meet each other in this quite remarkable paper by Cermello in 1908. And in this paper, he says, in the present paper, I intend to show how the entire theory created by Cantor and Dedekind can be reduced to a few definitions and 7 principles or axioms which appear to be mutually independent. And he proceeds to introduce what we call now Cermello theory, and then which was kind of made with addition of few axioms and some making some things more precise was then became the ZFC, the Cermello-Frankel set theory. So if we if one doesn't try to impose on us the view that Zermelo-Frankel theory is a theory of everything, then one can look at this theory, and this is quite a remarkable and very elegant and interesting theory, and also a useful one. But as I would argue, it's not exactly what Zermelo claimed it to be. I mean, I would say that it's not an adequate formalization of Cantor's theory, and that's one of the key points of tension, kind of, in what's going on now. So, but at about the same time, we see that Bertrand Russell, he was probably very, he seemed to have some kind of remarkably strong opinions about things. And here he writes, for example, that pure mathematics is the class of all propositions. That he gives a definition in the first paragraph of his work. What is mathematics? So pure mathematics is the class of all propositions of the form P implies Q, where P and Q are propositions containing one or more variables, the same in the two propositions, and neither P nor Q contains any constants except logical constants. And I guess this is kind of as concise and perfect expression of logicitism as could be found. So, and then of course that he proceeds. So this principles of mathematics is not such a big book, but then it evolves into the Principia Mathematica eventually, many years later actually. But and this effort to reduce mathematics to logic, which of course Russell here claims to have done, and which of course to some extent Zermelo here claims to have done for a subset of mathematics, namely for the Cantor's theory. They were, my understanding is that they were really motivated by this, also actually Platonic to some extent, idea of hierarchy of sciences, and that there are more perfect sciences and less perfect sciences, and you can find it in Proclus, discussed quite in detail, and that in this ideal view of things, the less perfect sciences should take their first principles from more perfect sciences and, in a sense, should be deduced to them. And that's what these guys were trying to achieve. I mean, they were trying to realize this great and ancient vision. And for them, logic was higher in the hierarchy than mathematics, so mathematics had to be had to receive its first principles from logic. But fortunately, I think, for us, a development in foundations too has put an end to that. And the development was due to Kurt Gödel, who in the fall of 1930 presented two theorems, and the first theorem, and then a few months later the second theorem, which are known today as the first and the second incompleteness theorems. And the first one, of course, I mean, volumes have been written about various interpretations of these theorems, but I would say that the first theorems basically implied that none of the known approaches to formalization of reasoning could be used to create a consistent formal deduction system where all questions about finite integers, natural numbers, could be answered. And of course, it doesn't exclude the possibility of some kind of entirely new approach to formalization which could achieve it, but if nothing in the realm of what we can imagine at the moment can do it. And the second theorem implied that if we have a system, a formalization system where even the basic questions could be answered, then such a system couldn't be proved to be consistent. By proved to be consistent, I mean proved actually in a weaker system. I mean, what Gödel proved in the case of a particular system of Principia Mathematica is that the system, and then it was translated into piano arithmetic, but he actually worked with the Principia system in his paper, that that the system cannot be proved to be consistent inside itself. But if you think about it, that's kind of that's an overkill. That's kind of a big overkill, because if the system is inconsistent, then surely everything can be proved inside it, including its own consistency. So if you can prove the consistency of a system inside this system, it really doesn't prove its consistency. Because if it was to start it inconsistent, then you would surely be able to do it. So he proved that something is impossible, which even if it were possible, wouldn't be sufficient. So he really proved a very, very strong result. And I gave some, I gave a long lecture a few years ago. I tried to come to grips with this myself and spent many hard hours and days and more trying to understand how is it possible that we know that something is consistent, and we also know that it's impossible to prove that it's consistent. Because this kind of does make sense. If we know something, we must be able to prove it. I mean, how do we know it if we cannot prove it? And so, and I would be going in circles in this. If I hadn't told myself that, okay, so we don't know that it's consistent. That's the answer. That's the only possible answer to this seeming paradox, that we do not know that something like piano arithmetic is consistent. We believe that it's consistent, but it's entirely possible that this belief is false and that it is not consistent. And so I gave a long lecture. You can find the I don't know if I have yet slides on GitHub, but there is a video recording at the Institute for Advanced Studies webpage, which is called "What if the current foundations of mathematics are inconsistent?" Where I discussed this for a long time. Let's start with that my understanding is that something like piano arithmetic can very well be inconsistent. And now let me try to explain to you why I'm still standing and not lying on the floor, kind of. And so there was this long lecture about it. And indeed, one can seriously consider such a possibility, and that would not mean the end of mathematics or the end of the world. So probably this result by Gödel, just maybe it was a little bit like when Pythagoreans discovered, one of them, I guess, discovered that the square root of 2 is irrational. That's what I wrote here in the language of Greek mathematics, that no multiple of the diagonal of a square can be measured by the side of this square. That's how they would say it. So that's the square root of 2 is irrational. And for them, it was the end. Well, it's not entirely the end of the world, obviously, because they continued living. But apparently, they had a model of the world in which everything was so beautiful and everything was based on ratios of various integers. And then this model kind of had to be pushed to a lower status. And something like that, I think, was happening here with Gödel. In this case, not with the model of the world, but with this relative positions of logic and mathematics, because he kind of showed that at least to the kind of logic which we nowadays restrict ourselves to, we cannot reduce all of the mathematics to it. So now let me fast forward. So that was a little story about Foundations 1 and Foundations 2, and how both of them developed in a remarkable way in the 19th and early 20th century. And then they tried to come together. On the one hand, one coming together was in Zermelo's system, another coming together in a sense was in Gödel's results. And now I sort of fast forward to when I was beginning to actually learn mathematics. And what did I see? So what I saw was that, well, of course, I didn't know at the time that it's a new vision of foundations. For me, it was the only vision of foundations. So I learned that mathematics is based on the theory of sets, that there is an hierarchy of concepts which one can kind of learn from reading Bourbaki, for example, except don't look into the first volume. So finite integers and operations on integers were defined in terms of finite sets, and arithmetic therefore could be reduced to the study of finite sets. Axiomatic geometry was non-existent. It stopped being a part of mainstream mathematics. Instead, there appeared fields of topology and differential and algebraic geometry. The division into the study of discrete versus continuous also didn't show up so much, because most of the interesting mathematics was about using one to prove results about another, and in practice it was achieved through the definition of continuous in terms of discrete using the ideas of actual infinity. And this approach to Foundations 1, so this total restructuring of what are fundamental concepts, what are all this Pythagorean division into 2 and then 2 kind of was gone, and instead there was, well, not kind of, it was gone from real professional mathematics, and instead there was this new system built on set theory, and that was extremely productive and successful. So what about Foundations 2? Also by the time when I started learning mathematics. And so here the situation is more kind of complex, I would say. So that is how I see it now. Of course, back then what I saw was that, okay, so you want to know Foundations 2? Okay, here is a book by Yuri Vanchmanin on mathematical logic, which explains what is what are logical propositions, quantifiers for all and exist, these logical connectives, the rules of inference, and this is the meta mathematics. Then there's the postulates of ZFC, and this is the second part of meta mathematics, and then everything else is reducible to that. And that was the beginning and the end of it. So it was accepted that set theory is formalized in ZFC. There was the first postulate. Well, and as a consequence of that, there was a postulate that the only acceptable formal language for pure mathematics is the language of predicate logic. And that Foundations 2, from the point of view of pure mathematics, had stopped in the early 20th century. When predicate logic was invented, there was nothing more to invent, and when ZFC was invented, there was also nothing more to invent, and that was the end of it. That's what I saw. Now, as I only started to learn like 10 years ago, the actual situation was entirely different. So actually, the second half of the 20th century was a period of unprecedented innovation and development in Foundations 2. Almost all of this development occurred outside of the area of predicate logic and were entirely invisible to pure mathematicians. So they were, almost all developments were due to, or maybe even all, were due to appearance of computers. And here is my kind of very basic analysis of sure. Well, let me read through this slide, and I'll give.
This is a claim, so remain virtually invisible.
well, I cannot give an example of invisibility. Um, so the dependent type theory, starting with the works of de Bruijn on the automass and continuing into the constructive type theory by Per Martin-Löf. The development into the general theory of syntax and semantics of programming languages. In fact, I mean, I would give the Martin-Löf type theory as an example which relates directly to mathematics, as we now understand. And more generally, I would just say that the whole theory of programming languages is actually a direct development of what of Foundations 2. And what happened is that the Boole and Frege, they both wanted to have a formal language for expressing human thought. And it was kind of, they did a great job of it, but then when computers came to the picture, people actually had to develop practical languages, because computer only understands formal language. It doesn't understand anything else. And humans had to communicate their thoughts to computers so that computers could perform tasks based on these thoughts. So they started to develop these programming languages. And these programming languages are ways of translation of thought into formal languages. So that's on a very general level, but on a particular level, I would say Martin-Löf type theory. So kind of the most important development with all of the with its then there was calculus of construction and calculus of inductive constructions. These were all formal systems which were designed to, in particular, to express mathematical things, and which remained completely invisible to pure mathematics, because they went entirely outside of the predicate logic. So that's how I see it. And it's there are actually more things. I mean, I just don't know everything. I mean, about this period, because I grew up as a mathematician. I didn't learn these things. I only learning them now. I don't know programming language axiom. So I mean, there was some development which was related to the predicate logic. For example, the development of this work by Robinson, I think, on the development of the resolution method of proofs. That was a very interesting advance in predicate logic, where new methods of proving things were developed, which were specifically developed for the convenience of computers rather than humans, and which are now which computers now can use, and they can do amazing things about proving things in predicate logic theories with these resolution algorithms. Not about resolution.
And what about this other guy who committed suicide? The one who was trying to be like Snow White. You know, the English.
Oh my God. Sorry. Yes. They certainly worked on it, and but I'm talking a little bit about a later period of time, about the second half of the 20th century. They worked closer to the first half of the 20th century.
But this sort of question is not a question of time.
No, but it's just this slide is particular. The second half of the 20th century was a period of unprecedented innovation. So we were discussing things related to this slide. So here it's I have repeated it myself that the advances of mathematics in the 20th century, in the second half of the 20th century, and they were great, fantastic advances that were due to the establishment of strong foundation in the form of set theory. And now I want to say it slightly differently, and to correct in particular myself. I think that the notion of a set, which is the simplest case of a general form, is absolutely fundamental for mathematics. And the main concepts of set theory, which were discovered by Cantor, such as the concept of bijection, for example, which was one of his inventions, they truly belong to the deepest level of the modern hierarchy of mathematical concepts. That this is definitely what made modern mathematics possible. However, I would also argue that the theory of sets have never been successfully formalized. That the ZFC, and I will be talking more about it and in more detail in this lecture and in the following one. So ZFC, I would argue, is not an adequate formalization of the set theory which is used in mathematics. And I believe that it was impossible at that time to formalize set theory properly because such formalization required much more advanced foundations too than were available at that time. In particular, it cannot be performed in the framework of predicate logic. It's just not possible to formalize set theory as it is used in everyday mathematics in the framework of predicate logic. And I would also argue that now a better, at least, well, adequate or not, but a better approach to formalization became possible. And most likely, first such formalization is being achieved in the framework of a more general theory of form that univalent foundations are based on. And I think that's the end of my plan for the first lecture today. Thank you very much.
For questions, are there any questions?
So actually, this is becoming. Excuse me.
I'm sorry. You.
Oh, me? Oh, thank you. So this is beautiful, and if I understand you correctly, there is some kind of. Can I put it? You're telling us stories about mathematics and the logic of mathematics. And both of them have a kind of meta differential geometric interpretation or representation. If you think what you mentioned on the slide about Cantor and Riemann. Because you're talking about forms, you're talking about differential geometric concepts, but you lift them at a meta-mathematical level.
Yes, this is one of the lines of current investigation, whether or not we can actually integrate the concepts of differential geometry and kind of continuum on the meta-mathematical level. I'm actually only mentioning it as one of the current lines of development. What I'm talking about is more over something which we discovered to be on more fundamental and kind of lying deeper than this differential geometrical things, which is the homotopy types, and they're lying deeper in the hierarchy of things than the continuous things, and that's what we understand much better now. This direction into the differential geometric things is very, very speculative at the moment.
But it is meta-mathematics, it's not mathematics.
The idea is to integrate something like differential geometry into metamathematics. Yes, one of the ideas. Yes, yes, there is such a thing.
I've got a question that partly relates to something you said yesterday. You observed that the hierarchy used to be logic and then mathematics, and logic is a more foundational science, and then you remarked that Gödel reversed the hierarchy. And I just wondered, this could be understood in two ways. One way would be that Gödel proved once and for all that you cannot base mathematics on the allegedly more secure foundations of logic, because the project of logicism fails. But you could also take it in another way, namely that in Gödel we find a pursuit of logic or meta-logic by means of mathematics. I mean, because he proves his results through, Gödel numbers and, through a kind of arithmetization of meta-logic. So I wonder whether both of these interpretations of your remark that Gödel reversed the hierarchy are correct.
Yeah, as I say, Gödel's work is kind of a result of this continuing intrusion of mathematics into logic. So it's eventually, on the one hand side, it was kind of telling, well, the Gödel's result on the one hand side said that logic as it exists is not sufficient to encompass all of the mathematics. On the other hand, it showed that mathematics can contribute significantly into logic, and that mathematics can help logic to develop. So I wouldn't really say that it I don't know whether it reversed the hierarchy or it just made it kind of undetermined. But yeah, so both things, of course, yes.
But then, does it make sense to speak of hierarchy?
Yes, of course. You mean hierarchy of sciences or hierarchy of concepts inside in science? Well, in that sense, probably doesn't.
Okay. As far as I understand, Gödel's incompleteness theorems, they are somehow universal, right? So if you say that with univalent foundation is the more proper way of looking at mathematics, how do you circumvent the universality of Gödel somehow, which says that you always will have incompleteness somehow? Or am I maybe you're going to talk about this in the third lecture? But
well, no. We don't circumvent it. Instead we accept it, and we say we don't circumvent it. Instead we accept it. We say that it is so, and it will be so forever. And well, maybe. I mean, who knows what will be forever? But we accept that in the nearest future it will be like that. And I actually have a special slide about it in the next lecture, about this particular issue. I hope I'll get down to it.
Can I make a local remark? Zermelo, in 1908, was here, a professor at the University of Zurich. And the University of Zurich was housed in this part of the ETH. So we are right back at the source here.
Yes,
very interesting paper.
Yes, I couldn't help noticing that in this last part of the talk about the second half of the 20th century, you didn't mention the word category. And certainly, I mean, category theory was a very important tool for the new aspect of Foundations 1, I guess. And many people tried to make it into a tool for Foundations 2 as well. So...
Yes. So actually I have, let's see. So I actually have a slide about it in the next lecture. I wouldn't say that it went into Foundations 2 all that much. Until the paper of Michael Mackay, which I also mentioned in the next lecture, who showed that the dependent type theory, the idea of dependent types and dependent sorts, is what one is what one needs in order to properly formalize category theory. That was his observation, that ideas from Martin Löw type theory can be combined with category theory in a very elegant way. But until that time, but even then, the category theory was not so much foundations 2. It was always kind of a part of newer foundations 1, and a very important part. And we'll see how it's actually a part of foundations 1 in 2 different ways. And anyway, so I'll talk about it.
Okay, let's thank again for this second lecture.
Thank you.
And the third lecture will be at 4:30 again in this lecture hall. So see you again a little later.